All right, thank you. I'd like to start off by thanking my co-authors, Chris Goldfinger and Sam Johnson, who have been instrumental in guiding me through this work. Like he said, I'm going to be showing you today some of the data we've collected and interpretations from some multi-beam bathymetry collected and seismic reflection profiles on the offshore segment of the San Andreas Fault, which is a significant seismic hazard for Northern California. Just to give you the region where we're at is at San Francisco, where we're at right now. The San Andreas Fault moves northwest, moves offshore at Point Arena, and over the last 100 years since roughly the 1906 earthquake has been an area of speculation as the exact geometries of this, with increasing refinement with available seismic reflection data. It's been difficult to pinpoint the location and geometries of this because of the lack of seismicity following the 1906 earthquake. It has been relatively quiescent. But we do know through paleoseismology that the northern section has potential recurrence intervals of 250 years, and that this is still an area of active research. So what we did, just to remind you, 1906, even though this is unknown, models show that the offshore section had significant slip occur during the 1906 earthquake as a potential slip patch, which begs the question whether or not this is a typical style rupture for a 1906 or whether this can be independently activated. So if you were here earlier, Charlie Paul did a really good job of telling you why we are getting really good at mapping in the marine environment, and that we are trying to implement the advantages and approach to terrestrial mapping with the invention and more prevalence of LIDAR and with ground-based outcrop scale studies, that I don't have to convince you that the marine environment is now reaching that level of expertise with the technology. So the marine mapping environment has its advantages of quickly being able to collect seismic data without having to worry about terrain, the depot centers instead of erosion centers that are typical in the marine environment, and you don't have to deal with people that often. So we asked ourselves, just as Dr. Paul asked us, can we combine the strengths of working offshore but approach the resolution of terrestrial mapping? I wish I had his surgical device. So what we did was we got a boat and put a multi-beam transducer on it. We also collected a bunch of single-channel seismic reflection profiles looking at the top half second. That's what we recorded. And also what you want to do when you go out to sea is bring smart people with you, which here is Sam and Chris manning the computer and probably showing me something that I hadn't seen. So what I'd like to do for you is try to have a similar video as Charlie Paul and show you the wowness of the data that we have available to us. So as we fly here, we're moving offshore at Point Arena, and this is the fault zone here. And as it moves offshore, we have not as much of a surface expression anymore, but what I'll show you in a few minutes is all of these white lines are seismic reflection profiles that we've collected. The San Andreas Fault moves offshore and then moves and cuts Noyo Canyon here and elongates it and deforms it. It moves through a broad section farther offshore, and then it experiences a restraining bend before moving back onshore here at Point Delgado or Shelter Cove. And then in this northern section here is the Kings Rain Mountains, where there's been an area of debate of how the San Andreas changes from here to up to the transform motion in the subduction zone. So that's an area that we are actively thinking about and investigating. So just another view of this data set here's Point Arena and Shelter Cove, and Punta Gorda is where our data set ends. So we have 2,000 square kilometers of high-resolution multi-beam bathymetry. And my high resolution is not Charlie Paul's. This is an 8-meter grid right here that was merged with the 2-meter grid of the California State Waters Mapping Program. We collected over 1,200 fault crossings, seismic reflection profiles, and a number of fault parallel ones. And we collected them at 1 kilometer spacing. So what we have here is some of our seismic data unprocessed. So running it through some processing, we developed some very nice images of the San Andreas fault zone in the shallow subsurface. And through a number of interpretations and iterations, we started to develop this interpreted model of what's going on at the San Andreas here, with cutting the main strand cutting through to the surface with a scarp, with a number of subparallel faults to its west side, and a significant amount of subsidence occurring on its eastern side, which I'll talk about in a second. So just to give you what I want to do here is to give you an overview as we move through the fault zone and show you some of the data we've collected and the interpretations we've made. So as we move offshore, here just north of Point Arena, we see the San Andreas fault zone trending at a strike of 333, and in the seismic data we see westward thinning Holocene deposits that are slightly offset by the San Andreas. We see the San Andreas juxtaposing a bedrock unit on the east with what we've interpreted as a quaternary marine sediment package here to the west that's likely part of the Point Arena Basin that's further offshore. And so as we keep going, we see the fault zone continue to trend this way, but becoming more northerly in a gradual releasing bend. But we see along the fault these heterogeneities in the fault, with moving away from having faulting to the west, but we split into an eastern strand of the San Andreas here with significant uplift for 3 or 4 kilometers at the leading edge, the end of this paired bend or paired fault zone. We also see image really well these progradational Holocene sediments coming off of the Caspar Creek, and not in the fault zone restricting Holocene sedimentation to the west here. Continuing further, just another image of the highly emergent deformed fault zone between bounding the San Andreas and the eastern strand of it. And this section here has been interpreted as lots of paleo channels and fluvial deposits, and quite erratic, but having marine flatline deposits to the west. As we move further, we reach Fort Bragg here and Noyo River mouth here. That Noyo Canyon is imaged in our field area, being captured and elongated by the right lateral motion of the San Andreas fault. We were able to image within our seismic profiles a fairly substantial incised paleo channel that we believe is connected with Noyo Canyon. And using our mapping, we were able to project that, yeah, the canyon has been captured, elongated, and at previous times during sea level low stands that this system did connect with each other. And other than that, we are unable to age date this offset channel feature, though. But what we are seeing here is that the emergence of these basin sediments to the eastern side, and incised by the Noyo Canyon Valley. And within this larger sediment basin, these not active, but active in the recent history normal faults. Continuing on, we see we're now in the main section of the San Andreas fault within this basin that has been defined as a lazy Z basin because of a 9-degree releasing bend that the San Andreas passes through. We image these sediment marine basin deposits well within our seismic data, with the majority of the basin subsidence occurring on fault at the San Andreas fault zone, and this progressively steepening deposits here. We also continue to image these normal faults throughout the basin that are of discontinuous in some spots or extend for many kilometers in others, but they are not driving the main subsidence within the basin, whereas we see most of this subsidence occurring within at the fault zone. We see that we're able to image with the northern part of this basin, where we start to increase our amount of Holocene sedimentation, that we can image the last glacial maximum erosion surface and see that the San Andreas fault is offset roughly 8 to 9 meters here. So we're seeing a vertical deformation across the fault of roughly 4.34 millimeters per year of subsidence, or east side down vertical deformation at the San Andreas fault. And this, we've augmented this, our high resolution data set with a industry collected seismic line that clearly shows this half graben style basin, that with the west dipping basement unit here, that is indicating that the San Andreas fault has a significant normal fault, a normal component at this section. Moving past the basin, we now the San Andreas moves through a 9-degree restraining bend, where it's coincident with a rocky shoal uplift area that is named Tolo Bank. What we see in Tolo Bank is a highly fractured rocks that project out from Shelter Cove, which are interpreted as King's Range terrain deposits. So this is a continuation of deposits potentially from the King's Range, which is here, a similar unit here, but we have little constraint on that other than its fault bounded and projection from Shelter Cove. We also see sediment packages warping around Tolo Bank on top of a thick prograding wedge here to the west that's at the shelf break, defining the shelf break on the western side, with very thick Holocene deposits over 20 or 30 meters in sections. We also see still a well-defined San Andreas fault zone on the eastern sides of these. So just to speed up here, when we get to north part of it, when we get to the part where San Andreas moves onshore, we collected more seismic profiles up here to address the question of how the San Andreas fault might play into the King's Range terrain. This seismic profile here doesn't show much other than a thick Holocene wedge deposit and little faulting. Continue on to this deposit here in front of Big Flat Creek, another very thick Holocene deposits with no visible faulting within the marine sediments. But what we do image on the far western side is the incoming Mendocino transform fault that's offsetting young sediments here of unknown age and trending onshore at the northern end of our section. We think that this model here, which has been proposed and is in the Quaternary fault map, is not the case right now, since we did not image one, or it is not an active structure. The potential for the fault to be in the surf zone is also potentially, it would be a very elusive fault at that point, or that the fault, the San Andreas fault zone merges into the King's Range and becomes these thrust faults. But that is still an area of, because there hasn't been any definitive mapping of strike-slip structures in this area. So just what we can do now is look at the overall trend of the fault and see that we are in a large restraining bend, but within that restraining bend, we're in a large releasing bend. We have small sections of restraining orientations that cause local uplifts and deformation. But this area here, when you look at the big scale of the San Andreas, from Central California, you see lots of small variability until you reach this northern section where it becomes very different orientation, which is an interesting question to wonder about. And our sediment packages, we did an isopack map that is very informative that we can talk about later if you want to. So I'm running out of time. But we have collected a large amount of data, and we're going through it, and there's very interesting results that are being revealed. Thank you very much.